So I will discuss how to plan an EXES observation. I'm going to first discuss the instrument overview in generalities, the wavelengths that we are able to access, and the different spectroscopic observing modes and the trade-offs between them. Then I'll go into an example of a common observation for us, which is a high-resolution observation of a point source. So that will be where we evaluate the atmospheric transmission around that wavelength of interest and the Doppler shifts that have to be considered in order to achieve something on a difficult region of the atmosphere. We'll feed that data into the EXES exposure time calculator for a clock time, and then I'll instruct on how to put that into the USPOT proposal tool AORs. So EXES is a mid-infrared spectrometer that operates between 4.5 and 28.3 microns. We get to only about 1% of the operating wavelength, up to 4% of the operating wavelength at a time. So that surprises some people that we're not able to cover some of the very broad features in the spectrum in a single setting, those solid state features known from ISO and IRS spectra. We get resolutions anywhere from R of 1,000 to 100,000, so we can deliver up to 3 kilometer per second velocity resolution, depending on the particular spectroscopic mode selected and the trade-offs between them. So it is a cross-dispersed spectrometer primarily. The grading shown in the top left corner is a 40-inch long aluminum reflection grating. This is the echelon grating that's responsible for all the high resolution capabilities of EXES. Then it gets cross-dispersed with another reflection grating that can be rotated that we call the echelle grating. And that has efficiency high points at very high angles for maximizing the spatial extent of the coverage of EXES on a particular source region, and minimizing the number of orders on the spectral array. Or you can select the other direction of maximizing the instantaneous wavelength coverage. So between those two options, you can get a high-medium mode, a high-low mode, or you can bypass the high-resolution grading altogether for more sensitivity and only use the gold grading on the right for a medium spectrum or a low-res spectrum in a single order at a time. The medium and low modes are not as commonly used, but they still can potentially deliver resolutions that are considered high by most standards. The medium resolution mode offers between about R of 8,000 and 25,000. The instantaneous coverage is about 1%. And to consider this, consider sources that are coupled Jansky. This is in the case 5 to 15 Janskys over the entire wavelength coverage will get you about signal to noise 50 in an hour of integration time. So millijansky sources really aren't something that EXES can do in any mode. Low resolution is something that we're very much not optimized for, and we ask that, particularly for that you discuss it with the instrument team to make sure that it's feasible. The problems that we encounter are that the background is really high and challenges the detector readout, and the fringing becomes a problem too. But nominally, that offers resolutions of about 1,000 to 5,000, and the instantaneous wavelength coverage is greater than what you get in the medium resolution mode. So to consider those broader features, solid state features, that's probably where you're going to end up, and then you need to discuss it with us. So high, medium, and high, low are really where we're optimized for narrow line work at high resolutions that benefit that kind of interest. So the resolutions in either one of those are entirely set by the choice of the slit width. So you can get R of 50,000 to 100,000, whether you're in the high, medium, or the high, low configuration. And the images that I show there are what you see in the detector of exactly the same spectral region, around 13.5 microns. But you see that the high medium is getting only 8 orders of coverage across the detector, but it's maximizing the length of the slit. Whereas the high-low mode is getting about 60 orders of coverage simultaneously, but the slit is very short. And in numbers, it's a 20 arcsecond slit on the left, and it's a 2 arcsecond slit on the right. What that means in practice is that you can observe, obviously, you can get 20 arcseconds on an extended source at a time in the high-medium configuration, or for a point source, you're enabled to nod the telescope in AB style to conduct your background subtraction. And that means that you get a √2 advantage in the signal to noise per clock time spent because you're always staying on the source. And you can't do that in the high-low mode because the slit is too short. So you have to nod to an off-source position and suffer some small penalty. So in point source sensitivity, in the same sense of getting a signal to noise 50 spectrum in about an hour, you need a source that's about 20 to 40 Janskis, depending on the wavelength for the high-medium mode, and you need to approximately take a factor of 1.4 less sensitive for the high-low mode. But the instantaneous wavelength coverage is where the high-low mode comes into its own, because for very bright sources, you can get about 6% of the operating wavelength in a single observation and scan a very, well, for us, we consider it a very big region of the spectral range at a time. So for the example observation, just a science motivation for this, there was a massive protostar, AFGL 2591, that was observed with the satellite ISO FWS back in the 90s. And it was seen that it had really abundant gas phase water in the rho vibrational band around 6 microns. But what it couldn't do was measure individual lines. The spectrum shown on the right is packed with blends, so you can't separate individual lines, and you certainly can't get any resolved line profiles unless they're extremely broad, which we're not. Getting the line width and resolving complexities to the line profiles could possibly hint at the location within what's probably a very complicated source and maybe a chemical origin of the water. So this is what we undertook in one of the commissioning flights back in 2014 with EXES. And to just give tangible goals for this, this example, let's say that we want to obtain a signal to noise 100 on this region with a R of 90,000 and cover about a dozen of the rho vibrational lines. And we want to center it so that we're sensitive to the ground state water lines so that we can see and be sensitive to the coldest gas. But a lot of times when you look at these sources in CO lines, you see a rotation diagram that breaks, indicating at the low excitations that you have a second temperature component that's very cool, and we wanted to see that for this source. So considering only that line for the moment, the first good step to do is to download an atmospheric transmission model from the ATRAN utility linked from the SOFIA proposal tools website. Give it reasonable values for a SOFIA flight, say 41,000 feet, flying altitude and a zenith angle of about 45 degrees. Give it the EXES resolution, which we're saying is about 90,000 here. And clearly, because it's a low-lying line and a low-energy line in the atmosphere of water, this rest velocity is completely hopeless, and you can't integrate them if there's no Doppler shift. What the model can tell you is that that line is about 62 kilometers per second wide. So in order to get some kind of decent chance to get any signal off of this, you need to have a separation of about 31 kilometers per second, either blue shifted or red shifted off of the rest line position. So the consideration that you have to make for this is what systemic velocities to the source is. So look in the literature, find an LSR velocity, convert it to a solar system rest frame velocity. I have these the tools that I use for this calculation in the next slide, but I won't go through it in detail. And once you know that it's on average being blue shifted by about 24 kilometers per second, look at the seasonal variations due to the orbital motion of the Earth and add it to that total. And just as an example, on April 1st, it kind of crosses the line where it's getting out of that less than 50% transmission zone of the atmosphere. So you can achieve 34.7 kilometer per second Doppler shift on April 1st. This slide covers the tools that I use in IDL to get to this point.
Curtis, you have about 10 minutes.
Thank you. So you take this information and you go to the EXES exposure time calculator, which is hosted by the UC Davis PI team, and it's linked from site. This is the first page that you get to when you access the exposure time calculator. It will ask for the rest frame wavelength or the rest frame wave number that you want to observe. You can enter either because the numbers don't overlap. It'll know what you're talking about. So I enter the rest frame wavelength of the ground state line, and then I check the box saying that I want to apply a Doppler shift to it because we care in this case what that particular line is doing. And I enter that blue shift of minus 34.7 kilometers a second. And then before proceeding, I select which mode, which of the 4 modes that we're going to use, which I've already decided was the cross-dispersed high-medium mode. So hitting submit leads to the next screen where you have a bunch of panels to enter information to further define your observation. The slit width is what defines the resolution of the spectrograph, but the design of the spectrograph was built for a much better imaging observatory than what was actually achieved. So slits, some of our slits go down to 1.5 arc seconds, which lose a lot of the PSF from the 2.5 to 3 arc second delivered imaging performance. So keep that in mind. The ETC knows about this, but you might want to check the signal to noise at different slit widths. For this, I'm deciding to trade off the signal to noise with getting a resolution of 90,000. So I've decided to select the slit width of 1.9 arc seconds. Next, you get to decide which cross dispersion order to observe in. And this isn't as much of a choice as it looks like, because as it happens, the efficiency of the grating is highest near its blaze angle, which is around 60 degrees. So it's better to get a very high order. Go ahead and try the ETC at different orders, but you'll see that it has a fall off as you go to lower angles in the sensitivity. But the other reason you want to go to a higher cross dispersion order is because you're maximizing the slit length. And as I was saying before, at a certain point, you can begin to consider knotting the source on the slit so you can do your sky subtraction all while staying on the source 100% of the time. This particular case that I selected is kind of a dividing line. At 10 arc seconds, we can almost do it without any real problem, but we could probably still do it and have a little bit of flux cancellation between the A and the B beams once the beams are subtracted from each other. But we recommend the more conservative case, but in actual execution, we might do a knot on slit for this observation. So finally, you define the signal to noise ratio that you want to get on this part of the spectrum. We said signal to noise 100, and that refers to the binned spectrum after it's been binned to cover 2 pixels over the resolution element, so Nyquist sampled, and you still get the resolution that we said, 86,000. And then you put in the source brightness, which from the ISO spectrum was 400 Janskys. So it's a very, very bright source, and this will be a very quick observation. So after hitting submit, you get an observing summary that pops up, including all the most relevant things for what defined the observation. And it'll spit out a EXES clock time. This is the time spent with the accounting for nodding off source and the latencies of the detector computer, and it also includes nod settling times. So this is a clock time as known by USPOT. You put this in for your integration time. in place of what other instruments call integration time, we call clock time. USPOT will add additional calibration overheads. The other thing that the screen, the final point of the ETC gets to is a signal-to-noise spectrum. This shows the entire spectral region covered by your selected grading configuration. And we see that we get, at the position of that ground state waterline, we get that signal-to-noise ratio of 100. But because that's a particularly B-set part of the spectrum, the rest of the spectrum is actually doing much better than that. So going into USPOT, you put in, when you're making an AOR, this is what you're entering. You're entering the EXES clock time determined from the ETC, that's 755 seconds. And then, because this is a point source, there's going to be a procedure where we nod the slit, or jog the slit around the position of the source until we maximize the flux coming through it. This can take somewhere between 5 and 10 minutes. And then there's an additional overhead for precisely getting the wavelength range requested, because motors don't always move like you think they will, so we can do a quick evaluation of the sky emission spectrum and make sure that we're in exactly the right place. And USPOT will choose to add those, but you can select to turn them off by hitting no peak up or no wavelength setup. And that would be in the case, in the former, if you have an extended source and you have no need to peak up, or if you have no real constraint on, say, plus or minus 200 kilometers a second in the center of the range of the spectrum is going to basically get what you're looking for, whether you tune it up or not. So this is what the observation actually looked like in real data. And you're encouraged to contact the instrument team for advice. This is where the help desk will lead you anyway, so I just give you these people's email addresses directly. Matt Richter is the PI at UC Davis and has a team of postdocs running the instrument. And USRA has me and Ed Montiel as the support scientists who have a lot of experience also running the instrument. So feel free to contact one of us, all of us, and get our recommendations. And that's it.